Professor Sharma here. In today's lecture video, I will be discussing about the fundamentals of radiation therapy. So, lecture 1 we learned a lot. Now, let us go a little bit more depth on the fundamental of radiation therapy to treat the cancer. First of all, let me begin with the simple question. What is electromagnetic radiation, EMR? So, the electromagnetic radiation is the fundamental aspect of physics, and it can be applicable for different technologies in our daily life. So, it encompasses the wide spectrum of the wavelength or the frequency, from the long radio waves to the short gamma rays, and these waves are created by the movement of the electrically charged particle, which is oscillating on the electric and magnetic field. That is why it is called the electromagnetic radiation. Okay, you can see this picture, the different spectrum of the radiation from very short wavelength to the high wavelength, very short frequency to the high frequency. Depending on their frequency and their wavelength, their energy is different, you can see here. So, basically in short, I can tell you that the radiation is the emission and propagation of energy, you can tell that, okay, which can propagate through the space or the matter or the material medium, and it can be in the form of the waves like X-rays or maybe the gamma rays, or in the form of the particle. For example, we can call that is alpha particle, beta particles, electrons, protons, neutrons, and so on. Okay, these are the electromagnetic radiations. So, basically when in the medical physics, in the radiation therapy to treat the cancer, you have to be familiar with the ionizing and the non-ionizing radiation. So, the radiation can be divided into two parts. One is the ionizing and another is the non-ionizing radiation. Okay? So, the ionizing radiation means when the radiation or the particles or the wave hit the material, it has sufficient energy, hit the matter, it has sufficient energy. When it hits that matter or material, it can knock out the electron from that matter, that can remove the electrons from the atoms, and they can create the ion. Any kind of the radiation or the wave or the particles that can clearly knock out the electrons of the material or the matters, these radiations are called the ionizing radiation. For example, the X-rays, sufficient amount of the X-ray, energy of the X-ray, if you hit maybe in the body, it can knock out the electrons and make the materials or the atoms ionize. Okay? Gamma rays are high energetic, they can also knock out the electrons very quickly, and the protons and electrons, all they are the ionizing radiation. But when I will say the non-ionizing radiation in medical physics, so non-ionizing radiation cannot knock out the electrons directly. It cannot knock out, but it can excite the electrons of the mediums or the materials in which it hit. For example, the microwave. Microwave is the example of non-ionizing radiations. The radio waves, infrared, right? Maybe the ultraviolet A and ultraviolet B. C is a kind of border between the ionizing and non-ionizing. I would say there is ionizing, ultraviolet C is, but ultraviolet region A and B is the non-ionizing radiation. So, in radiation therapy, we use the ionizing radiation because it damages the DNA, because we wanted to kill the cancer. To kill the cancer, we have to damage the cancer DNA, and for that we need to use the ionizing radiation. So, here is the table I am going to display here, the type of radiation in radiation therapy you can use. This is very important table. You can see here we have the X-rays that we call the photon. When I say the photon, that is the X-rays, that is the light. Actually, we use the light, a small particle of light we call the photon. So, in radiation therapy we use the X-rays for the external beam radiation therapy. We call that is EBRT. Look at this terminology, external beam radiation therapy, that is called EBRT. Basically, when we treat the deep seated tumor, for example, in the body, there is a tumor in the deep inside the body, then we have to use the X-rays. So we use the X-ray with the 6 megavolt, we use the 10 megavolt and the 15 megavolt to treat the deep-seated tumor by using the X-ray. In some instances, we have to use the electrons. Okay, for example, superficial tumors. Okay, maybe the skins, maybe the breast, or maybe the chest wall. To treat this kind of tumor, we have to use the electron as the radiations in radiation therapy. So when we use the electron, we have to use the 6 mega electron volt, or 9 mega electron volt, or 12 mega electron volt, or 15 mega electron volt, or 18 and 20 mega electron volts. Electron energy is used to treat the cancer for the superficial tumors. But some instances we have to use the proton. Okay, so generally the proton, very high energy, 250 mega electron volt of the proton can be used. For example, so many kids nowadays have the cancer, and we have to spare the healthy tissue, and we have to kill exactly where the tumor is located. So those instances, for example, in pediatric cancer, we use the proton therapy. And maybe the tumor near the critical organs, maybe the brainstem, or maybe the critical organ. Okay, these organs need to be spared, these organs need to be saved. So in that situation, we have the proton. There is a Bragg peak. I will come to that point. What do you mean a Bragg peak? Why proton is used there? And in that instances, we're going to use the proton as the radiation therapy. But some instances, we're going to use the gamma rays to treat the cancer. So maybe in radiosurgery, we will discuss about the gamma knife. We'll come to that point. We'll discuss about the gamma knife, or maybe the high, dose, radiation, brachytherapy, or the low dose radiation brachytherapy, depending on the source of the gamma rays. Maybe you can use the iridium 192, or you can use the iodine 125, or the cesium 131, depending on the source of the gamma rays. These gamma rays can have the different energy sources. Maybe the cobalt 16, that is important one. So it has 1.17 to 1.33 mega electron volt energy range. So these are the types of radiation we're going to use for the to treat the cancer. Another question so many people might have, why we are using these different, we're going to use, when we're going to use electron, we're going to use proton, when we're going to use the photon, when we're going to use the gamma rays. So let me discuss about that. For example, the photon, when you're going to use the photons, maybe the X-rays, when you have a deep tumor, maybe the lung, in the brain or pelvis, okay, due to the deeper penetrations and the skin sparing, because we want to spare the skin, because if the tumor is inside, we don't want to destroy the superficial region, for example, skins. For the electron, so we have to use the superficial tumor. I told you that, for example, the skin, maybe the chest wall, because it limited the penetration, because the electron, I will come to that point, what happens there. And in proton, you can see the critical structure like brainstem. So the tumor nearby the brainstem, we have to protect that. So we have to use the proton. Maybe the eye. So back of the eye, and it's a very critical region. So you have to be very, very precise, and the radiation exactly hit that and spare the remaining surrounding, organs or tissue or the cell. Okay. So because of the Bragg peak. So the gamma rays also the precise ablation, we can say that, maybe the brain metastasis. So use the gamma knife. It's not a knife, it's very precise without taking out the skull or anything. So you give the gamma ray, and we can give the localize, we can implant localize also. So the neutron, it's not nowadays used because the radiobiological effect of neutron is severe. So we are not using the neutron, but we rarely we can use for the neutron. Maybe some kind of the radio resistance tumor, for example, the tumor in the salivary gland, that is very less sensitive. That's why we give the neutron. So in those instances, we can use the neutron. But why we use the photon for the deep very sensitive part we use the proton, and for the superficial we use the electron. For that, let me go this curve. Okay, we have a dose. You can see the dose as a function of the depth of your body. Begin with the skin, right? Begin with the skin. So in depth in millimeter and the dose in maybe in the gray or whatever. So you can see here in x-axis you have the depth in each tissue from 0 to 15 centimeter. You can say that, and y-axis you see the relative dose delivered during the external beam radiation therapy. So if you look at the electron, we can see here the electron with the 4 mega electron volt, okay, which is the purple dotted line. You can see here the behavior. If you look at the behavior of this line, it deliver most of these doses near the surface, around 1 to 2 centimeter. Okay, then you see here then it drops sharply to 0 because it immediately deliver the energy nearby the skin, and then penetrations it goes deep, there is no energy, almost 0. So yes, easy, right? It's good to spare the internal tissue. So so penetration is very shallow, okay, less than 3 centimeter deep, I can say that. And basically superficial tumor, maybe skin cancer or chest wall cancer or some kind of scares, we use that one. But remember that the abrupt fall off is advantage for the sparing deeper tissue, right? Remember this fact. If we go the low energy X-ray, let's begin with the 4 mega electron. So you have the solid blue line in this figure. So if you look at the deep peaks just below the skin, you can see here the peak value is just deep below the skin, and then it gradually falls as it penetrates deeper, right? So it's still significant in the skin dose, though better than the ortho voltage. Ortho voltage means that you have very low in kilovoltage, not in the mega electron voltage. So penetration is a moderate. You can see may not reach the deep seated tumor effectively for the low energy X-rays, but it was used in the older technologies. But in modern therapies, we use the little higher energies for better depth control. Okay, but if you go with the high energy X-rays, maybe the 20 mega electron, that is the highest we can use here. Green dash dotted line you can see in this picture. So the behavior of this curve, you can see here the dose builds up below the skin surface. You see here in the skin surface there is no dose build up, but below the skin surface the dose build up and peaks at a few centimeter, and then it decreases slowly. You can see in this curve it decreases slowly. So skin sparing is excellent. You can save the skin and superficial organs. So built up region spare skin from the high doses because we wanted to spare these organ. So penetration is deep. So nowadays we gonna use most commonly used in the linear accelerator for deep tumors. We use the high energy X-rays. But for the proton, you can see in the red dash line. So behavior is low dose at entrance. You can see here when it enter, the dose is very low, and then immediately you have a sharp bragg peak. You have a very concentrated energy at a very local point, at a specific depth, followed by an abrupt fall to 0. Then immediately 0. That means no further penetration after that bragg peak. So that's good, right? It can be controlled via precise way, maybe 10 to 15 centimeter, and tumor near the critical structures like brain stems, eye, or pediatric cases, the proton therapy is very useful, but it's very expensive. We have very less proton center in the United States. Even in the United States, we have very less proton center. Okay, so very expensive. So the key benefit of this proton therapy is it provides the maximum dose is delivered only in the tumor and is sparing the healthy tissue before and after that peak value. So that's why proton therapy is very important thing. So that's all for today. Thank you.